I'm glad to see a full room. Thank you all for coming. And I'm Pavol Kollár, and I'm a third-year student of Tatiana Eceva. Today I will show you something that I've been working on, especially in the past few months, but we'll also recap what I've been doing in the first 2 years. So the structure of the presentation, the first two sections of the presentation are devoted to this earlier problem, and I'll report on the progress that I've made so far, or rather since I last spoke here. And the latter two sections are for the new problem. So let's get right to it because there's plenty of material to go through. The main character of the first problem is a graph, which is a pair of two sets. The first set is the vertices or nodes, and the second set is the edges between them. And we insist that the edges are between pairs of vertices and specifically pairs of distinct vertices. There is no edge that goes from one vertex back to itself. We don't allow that. And the crucial notion within these graphs will be the graph automorphism, which means that if we are given a graph, the automorphism is a function on the vertices, specifically a permutation of these vertices, such that it preserves the adjacency and non-adjacency in the graph. What this means is that if we shuffle around the vertices while keeping in mind which vertex is connected to which, the overall picture after we move the vertices should stay the same. For example, if we focus just on this hexagon and square shape, we can reflect the vertices along this axis, keeping these four vertices still, while moving this trio into this to create a graph automorphism, because the edges stay looking exactly the same as on the original picture. And you can have several more. For example, you can rotate this triangle around, and that's also an automorphism. And once you learn a bit more about group theory, you note that you can compose these automorphisms together to create a so-called group of automorphisms, where you collect all the automorphisms together and the operation is the composition. And the particularly nice graphs are the ones that, with these automorphisms, you can take any vertex that you want into any other vertex that you want. For example, if you say that I want this vertex mapped to here, well, I can just rotate the whole picture around, and that's fine. On the other hand, if I want to move this vertex to, let's say, here, I can sort of warp the hexagons inside out to keep the picture looking the same. And that's also an automorphism. And if this happens for a particular graph, we call it a vertex-transitive graph. And here's another example of a vertex-transitive graph, even though it doesn't look as clear as whether this actually is vertex-transitive or not. But in fact, this is the skeleton of the football, which should help hopefully convince you that this is indeed a vertex-transitive graph, because the vertices are these intersections of the binding, I think it's called, this binding, and indeed you can move any of the crossing of the bindings into any other crossing, while keeping the overall ball looking the same. In a particular subclass of vertex-transitive graphs are Cayley graphs, which are defined via a group. Namely, a Cayley graph is defined by a... What happened? Waiting in the lobby. Well, let's admit. Okay. A Cayley graph is defined from a group G and the subset of its elements S in a way that the vertices, oops, and now I lost focus of the PDF, whose vertices are the elements of the group, and the edges are dictated by the set S that we chose. Specifically, this is the Cayley graph of the cyclic group on 8 elements with elements 1, 4, and 7. In this case, you can interpret the Cayley graph or the group as addition modulo 8. So 0 moves to 1, 4, and 7 as described here, but 3 moves to something that's 1 below, 1 above, and across. So that's a Cayley graph. And these Cayley graphs are actually a proper subclass, i.e. all Cayley graphs are vertex transitive. That's an easy exercise. And this Cayley graph, this is actually a Cayley graph and also a vertex transitive graph, but this one is not. So it's actually a proper subclass. And the most famous example of this being not Cayley is this guy, the Petersen graph. And at this point, probably most people will say, okay, fine. This is how it looks like. We have a big blob of vertex transitive graphs and the smaller blob within of Cayley graphs. And we're fine with that. But as mathematicians are weird creatures, and we say that's not good enough, as I've been telling you for the past 2 colloquia, and we define extra layers on top of this. And this particular one was started by Jeanette Goyak in 1996, where she defined so-called quasi-groups. And the outcome of her paper will be now very butchered in what I'm about to say. But the gist of it is, well, actually, a Petersen graph is a Cayley graph, specifically for a particular quasi-group that is acting on pairs of numbers, which we won't specify for now because we are short on time. And then we get generalizing, because that's what mathematicians do. And the first generalization is from Robert Yaitse and Gareth Jones. And in their paper, they discussed more of the subsets of automorphisms, namely R regular families. We'll see what that means in a little bit. And so we know that graph is Cayley, a graph gamma is Cayley, if and only if there exists a subgroup within the full automorphism group that is acting regularly on the graph's vertices, right? We have the full group, and then we take some small chunk of it that still is required to be a group. And acting regularly just means that every vertex is mapped to every position in the graph precisely once. We call that to be one regular action. And the question that Yaitse and Jones asked and investigated was, what is the smallest R such that there is a subgroup G of the full automorphism group that is acting R regularly on gamma's vertices? So if we have a Cayley graph, we know that this R is 1. That's what that theorem tells us. It's actually a theorem. But for example, for the Petersen graph, this R cannot be 1 because it's not Cayley. In fact, it turns out that for Petersen graph, the R is equal to 2. And generalizing even further, we don't have to just consider these permutations or automorphisms as just being connected to graph. We can separate them and just think about them as permutations of elements, which is what Philip Kerag in his bachelor thesis did. And he actually used computer power to generate lists, complete lists of the R regular families on n elements. And this is one of the outputs of his work, where he summarizes how many R regular families on n elements are there. And you'll notice there is a lot of these red NGs, which means that these were not fully generated. And not because he was lazy, but because the numbers, as you can see in the row n equals 5, they grow very, very quickly, from 1 to 1,000 to 11 million, and so on. It keeps going like by 3 or 4 digits each time for a while. So when I got here and saw this problem, what I thought that let's not generate them right away, because that might be infeasible and silly. Let's try to first verify how many of them are there. And if it's a reasonable amount, then we can think about whether we want to generate a full list. At which point these guys entered the game. We introduced complex numbers as well as Fourier transform, which is a ubiquitous tool in many branches of physics and in maths as well. And specifically, I took it so far, the algorithm, that it's now computing at the Clara cluster at our faculty. Specifically, well, I wanted to go there much sooner, but because of some unexpected delays, I only managed to get it started last Friday. And today, when I came in, I was checking the files, the output files, and it was still going. And I estimate it will still be going for like 2 or 3 weeks. at which point I hopefully will have a concrete answer to give you. And also, in the meantime, I was writing a paper, this is it, which is not fully finished, but we're working on it. And before we move on to the second problem, I wanted to mention a few other things that were part of this project, at least on the surface, because there's a lot more interesting rather than just doing the Fourier transform algorithm. There's more to it. So first of all, we tweaked a famous algorithm that counts the number of leaves in a tree to heuristically estimate the number of our regular families on 5 elements. And here we have the mean of, I think, either 50 or 100 trials of that randomized algorithm. And here we have the true counts, where the greens are the extra ones that we gotten from other computations. And later on, we do not know the exact count, so even the ratio between mean and exact is not known, but note that for the ones that we do know, it's quite accurate. It's only like 4 or 5% off, which gives us a strong intuition to conclude that there is roughly 10 to the 24 regular families in total on 5 elements, which confirms our skepticism, let's say, to not generate them right away, because this kind of lists of these lengths will be completely unfeasible to store in a computer at all. And one more part that is interesting here is how do we pick good parameters for the program that I fed to Clara, which is where it's convenient to switch from just permutations to their matrix representations, which is something like this, when we have, it's almost a zero matrix, except for the entries where I is mapped to J, that's when it becomes number 1. And if we have an R regular family, then summing up the matrices, the permutation matrices that are in this family, is necessarily the constant matrix with entries R, because, well, that's the definition. An R regular family is a family where each permutation is taking every element to every other element precisely R times. I know that's a mouthful. And so now we can check via just these matrices and not concern ourselves with the computation, the heavy computation of Fourier transform directly. And there are a couple of conditions that we need to check, namely that the matrices are sum of distinct permutation matrices, and also because of what the Fourier transform does, it needs to satisfy this kind of scalar product condition. And once we run this for long enough, we can get some viable sets back. This particular set is actually the one that's running on Clara right now. And there are a few more. This one was run by us already and allowed us to compute the green numbers that you saw in the previous table. And here are a few more that are still waiting to be processed. Also at Clara. Coming to you in the next month. All right. So the future directions is, well, first of all, finish that article. Second of all, get more computations on Clara. And with all the use techniques and the data obtained, I hope to produce one more paper from that, a very computation focused. And finally, for further research questions, we could ask, given any graph, or perhaps a graph that is of a particular class, what is the smallest R such that there is an R regular subset? We don't insist that it needs to be a group. What is the smallest R regularly acting subset on the gamma's vertices? And such a set is called an R regular family of graph automorphisms. And here we leave this first problem behind and move on to the next one right after a water break. I didn't put the elevator waiting music, I'm sorry. Okay, so secondly, the second problem is kind of image recognition but being very down to earth. And let's see an example of what I mean by that. Let's explore 5 by 5 tables of zeros and ones, such that nowhere in that table is there a 2 by 2 block that's all zeros. So for example, this one is good. It doesn't have any blocks of zeros. So is this one, but this one is not, because in the top left corner you have a block of zeros like that. We forbid that. And there is lots of arbitrary choices that were made for this one, so we can increase the size to, let's say, 9 by 11 or whatever, and also we can forbid more matrices. Again, for example, forbidding the block of zeros, the block of ones, and also these two patterns, which are sort of crossing diagonals of ones and zeros, those are not allowed as well. And when you start looking at the tables that you get, when you forbid this, you get this, I call it archipelago matrices, where you get a sea of ones, like this, and cut up from one another, there are some islands of zeros. Note that the ones don't need to all be connected via sides. There is an isolated piece of ones here, piece of ones over here, even here. But it still, at least to me, resembles some kind of islands and sea. So let's do a proper definition now that we've seen some examples. Namely that we have a fixed alphabet of symbols, A. Up until now it was just zeros and ones. And we choose a set, the Z, of forbidden submatrices that mustn't appear anywhere. The only thing that we insist on is that each of them has the same size, K times L, which can also be varied. And for a given positive integers, M, N, we want the matrices of that particular size that do not contain anything that's forbidden. This is what we call a boundary matrix. And to make our job a little bit easier, at least for the explanations, we just restrict ourselves to the binary alphabet, as were the examples before. And yes, you might object that that's too simple then, but you should think deeply of simple things, which is a motto I learned at Promise, which was a very nice experience in England. And our task, much like before, is to enumerate these boundary matrices and to discuss some of their properties. And before we get to the enumeration, in the abstract, I advertise that it is connected to the word problem or the word searching. But so far, I haven't said anything about words. So let's see what I meant. There is this notion called anti-dictionary languages, where we have a fixed alphabet A, much like here, and we take a few non-empty words into a set D, and then the anti-dictionary language is defined to be the set of all words that do not contain any word in the chosen ones as a contiguous subword, which mirrors what we have here in the matrices. In fact, these boundary matrices are the two-dimensional analog of the anti-dictionary languages. And the set D in this case, in this context, is called the anti-dictionary of the language. So, now the enumeration, the exciting part. Except there...
Is it a complement? No.
Sorry?
Dictionary, is it a complement of dictionary language or not?
That I don't know. I don't think so. No.
Probably not.
Well, depends on what you mean by dictionary language, because anti-dictionary has all the words that do not contain anything that's in the forbidden set. Whereas the complement of that would be contains at least one of those words somewhere in itself. So if that's your definition of the dictionary problem, then yes, it is. But I'm not sure what the proper dictionary problem is. Right. So the problems from trying to enumerate these start right away because of the sheer number of matrices. To produce a full list of matrices, we potentially need to enumerate exponentially many of them, which is a very big no-no. We cannot fit that anywhere as soon as the m's and n's start getting into tens, let's say, and by the time you reach 100, you run out of the universe completely. So we'll be satisfied with just counting, but even that needs to be done carefully, because we cannot just do the naive thing of, oh, here are all the matrices of size m times n over the alphabet A, because there's exponentially many of them, and so that will be intractable. So we need to be a little bit more clever than that. And the cleverness stems from the fact that if you have a boundary matrix and you already checked that it's boundary, then by adding one more column to it, the only thing that can go wrong in terms of being or not being a boundary matrix is that if the last columns of the established boundary matrix here and the new column create something that's forbidden. If that doesn't happen, then you are fine. And this allows us to use dynamic programming to get information about the boundary matrices with one more column based on the previous information, which was already done by Robert Jajca in an earlier paper and then revisited by the trio Jajca, Jajcejová, and Oppial in 2018. And what is this dynamic programming that I mentioned? For that, let's use the example of noise matrices, which are boundary matrices for the forbidden set of these matrices, where the asterisks can be either zeros or ones, we don't care. But there must not be any of these plus patterns of either zeros or ones. If that doesn't happen, then it's called a noise matrix. So the gist of the dynamic programming is that we take the last few columns, namely 2 in this case, and then we try to append new columns onto it. And we check whether there is a collision. So in this case, adding the column 1, 1, 1, 0, 1, 0 creates a collision because we have a plus of ones. On the other hand, these two columns don't create a collision, and this one also does create the collision. And so when we have a complete information about the previous case, much as you do in dynamic programming, you can try to append all new columns to all possible masks, as before, and you get the new count, which is precisely what they did in the paper. And that allows you to create a table of values, which is just the number of boundary matrices of m times n size. In this case, this table is the boundary matrices where you forbid two zeros to be next to each other in a row. Being below each other, that's fine. We don't forbid that. And if you look at the values, they may not tell you something right away, but let's focus on individual rows. For example, the first row you may note or you may recognize as Fibonacci numbers. The ones that you take the 2 and sum them up, you get the next one. You take the 2, sum them up, get the next one, and so on. And the latter rows are just the powers of the Fibonacci numbers in this case. Right? 2 squared is 4, 3 squared is 9, 5 squared is 25, and so on. Third powers, fourth powers, fifth powers, all the way down. And Jajca, Jajcejová, and Oppial showed in their paper that no matter which row you choose, if you just focus on that particular row, the numbers are bound together by a linear recurrence relation. So in the case of Fibonacci numbers, that's easy. You even know the formula. You take the next one is the sum of the previous two. That's a linear recurrence. But for squares, that's not quite so clear. But in fact, there exists a linear recurrence relation, in this case of degree 3, where you take 3 previous elements. And when you combine them together in a linear combination, you get the next element. And so on forever. So that's a theorem that was proved in a paper. But I'm lazy, let's be honest. And so I'm not satisfied with just this, that for any particular row we have a linear recurrence. I want just one recurrence that could be used in the whole table. And to make matters a little bit more easier on myself, I will allow it to not just look at the values in the previous values in a row, but also into the previous rows. So let's see how that looks like. If I want to calculate this particular entry, what I can do is not only look at these values before, but also at some of the ones above it, let's say these. So the question is, can I create a linear recurrence like this that considers all of these possible numbers to combine them into the next one? In some sense, I'm turning into Sauron in my search of one recurrence to rule them all for a particular table. And we'll revisit that, how well I do as a Sauron. But let's firstly look back at the dynamic programming. Because we said that when we have the particular information for number of columns n, we can get the information for n plus 1 columns by considering all possible masks together with all the possible new vectors. But that's tedious and takes a long time, so why don't we just do this analysis once as to what goes well with what, and then we can just use it repeatedly, which is where a new graph comes in. In fact, this time it will be a directed graph. So let the graph gamma m be the graph with vertices representing all m times L masks, m being the fixed number of rows that we said that we fix, and L being the number of columns in the forbidden matrices. And then there will be a directed edge between mx and my if the intersection is matching, I'll get to what that means, and these two masks do not create anything that's forbidden. But actually, this forbidden submatrix business is not really concerned in edges, but in vertices, because already the masks, not all masks are viable if we forbid some of the matrices. So, in fact, we need to toss some of the vertices away and then start connecting. So, for example, this can be a particular mask, and then let's examine what it can where do directed edges from this vertex lead to? There is not a directed edge back to itself because these two matrices cannot follow by one another. If they did, the last two columns in here would need to be the same as the first two columns here. Right? They don't overlap correctly. So this is a no-no. And neither does this mask lead to this one. This time the intersection is fine, right? These two columns are indeed same as this, but they do create the plus of ones which we forbidden in the noise matrices. However, this one, that's fine. There is a directed edge going from this vertex to this vertex. And once you create the whole graph, which can be pretty large because it has the number of masks in the size of 2 to the power of this number of masks, with some potential masks being thrown away by the forbidden matrices. And once you have this, any kind of walk along the vertex graphs, no, any walk along the vertices of the graph makes a particular boundary matrix. So you start at the vertex, you move, and then you kind of glue the masks that you saw together into one boundary matrix. And this can be counted by the use of the adjacency matrix of the graph, where you raise it to the nth power, which is the number of steps that you take, and then you sum up all the entries to get the number of boundary matrices precisely. That's a well-known property of the adjacency matrix. So, and once you do this, then we have a theorem that we proved, namely that if we have an arbitrary alphabet, for now this can be any alphabet, not just the zeros and ones, and we have the fixed set of forbidden submatrices, when we additionally fix the parameter m and consider the function of the boundary matrices, this time with only one variable, namely the number of columns, bn, there are 3 possible cases in terms of how the walks in the graph can look like. If there are no cycles in the graph, then when you start at a particular vertex, you can take a walk, but you can never return to a vertex that you've already seen, because that creates a cycle. And so, because the number of vertices of the graph is fixed, constant, if you start wanting boundary matrices of bigger size than what the matrix can provide to you, well, then there are no possibilities to have this. So eventually, it can happen that the boundary matrices just die out. There are no possible boundary matrices after a certain size. Secondly, the function can become a constant that's positive. And this can happen if you have just an isolated cycle with nothing else touching it. If there is a cycle, then you can create any length of words that you like. You just keep winding and winding around the circle. But the number of possibilities that you get is still finite or constant given by the number of vertices in that cycle, because you can only start at so many of them before you get the same thing. So that's number two. Number three, if you have, for example, two cycles that cross each other in some vertices, when this happens, the number of boundary matrices becomes increasing after a certain point. At first, it may be able to decrease a little bit, but if there are some cycles that intersect in the transition graph, you must eventually start increasing. And this, actually, allows us to prove another theorem, namely, that if you just forbid single row matrices, for example, the double zeros, when this happens, there are only two possibilities governed by these three. It can either become a constant, which mirrors one of these two cases, and if it becomes constant, then you must have the one recurrence to rule them all, because, well, after it becomes a constant, you just look at the neighbor to the left, and it keeps on going and going, and that holds for any row. However, if you are in the third case, then a nice argument using machinery like Vandermonde matrices and determinants allows you to prove that in the third case, the one recurrence does not exist at all. It cannot, because in fact, these numbers, especially when you move between rows, grow way too quickly for it to keep up. And one more thing that I advertised in the abstract was the De Bruijn graphs, which we haven't seen yet, and I'll show you why they pop up. Let's for now forget in the transition graph about these forbidden submatrices, and just consider the masks and that their intersection must be matching. This is precisely what De Bruijn graphs are, where you take strings of, for example, zeros and ones, and you make an edge between any two vertices that can follow from one another. So if you start with 3 zeros in a string, well, you can follow it up with either a 0 or a 1, in which case you either get 3 zeros, so the edge should go back to itself, or the 3 zeros lead to 3, 0, 0, 1, because that's like this possibility. And then you keep going. Right? You put 0, 0, 1, 1, 1, and so on. The De Bruijn graph is kind of scanning this string and noticing which triplets can follow from one another. And in fact, if you don't do the forbidden submatrix business here, this is just precisely the De Bruijn graph, because all the masks can be given because there are finitely many of them, it can be given a unique symbol, and then you just, well, are considering the strings of these symbols that are together. However, if you do now bring back the forbidden submatrices, what you get is that because it was a vertex property, now some of the vertices get completely erased out of the graph, which in the mathematician realm we call induced subgraph. You like scrub away the vertex and also all possible edges that go into it or out of it. And I'm hoping, but I'm not sure because this was only a very recent discovery, that somehow these De Bruijn graphs can help us gain additional insight. The De Bruijn graphs themselves are very popular, especially in the fields of, let's say, genome assembling and so on. And so one of the questions is, can these help us in our problem as well? Maybe. And secondly, I would like to characterize the sets of forbidden matrices for which there does not exist this one linear recurrence relation. So I don't want to become Sauron yet. Or if full characterization proves infeasible, at least identify large classes of sets that do not have this property. And that's all I have for you. Thank you so much.